I'd like to introduce our first speaker of the session, Professor Hans-Christian Langowski from the Fraunhofer Institute is going to start us off with a discussion about designing for circularity and safety aspects of recycled plastics packaging. The floor is yours.
Yes, thank you very much. This afternoon I will present my opinion on the different ways to look at design for recycling and all other types of design for. It's my opinion, you don't need to share it, and if you don't share it, we have time enough afterwards to discuss it. So first, the outline. So we have a lot of Ds. D for design for recycling. This was something we were talking quite a lot about in the last hours. We have design for circularity. Some people also have design from recycling, which together with design for recycling makes design for circularity. But what I would like to put up in addition is design for functionality, which is even as important as the rest of the Ds. So then I will talk a little bit about ways for assessment of recyclability, just to put up some key points and also some missing points there. Also, the regulatory aspects are a little bit difficult, and I will not repeat them, but only put up, for me, the most important issues. And then there will be some remarks about technologies, barrier technologies that are important to achieve the targets that we need to achieve. Okay, and also conclusions. Some missing links. There are still a lot of things missing in our concepts and an outlook. All right, so the first thing is something you will at once recognize that some of the figures are a little bit different than others that have been shown today. I took the figures from Plastics Europe for 2020. They are the only thing you can find, the only figures you can find, which are both valid for recycling of packaging materials and the usage of materials in package. So this, you have to go back 1 year. And if you look at those, you will see that the packagings in 2020 have been made with about 20 million tons of fossil-based plastics. There is a little bit of bio-based sources. This is a different numerical source from bioplastics, European bioplastics. In total, there were about 21.3 million tons plastics used for packaging. And if you look to the paths they go, you will recognize that there is a number of 16% which has not been specified. And the difference comes from the fact that I took this as 100% and not the amount that has been collected after being used. So you will, if you compare the figures, you will see some differences. And if you look at this, you will see that from this, about 27% goes to recycling, 20% goes into, about 20% goes into recycling for other products, which you may, by some justification, also call downcycling, and less than 7% go back into packaging. Different sources, different figures, but the overall image is that this is quite low, and especially those non-specified 16% are also a big question mark. Okay, the rest is clear. The question is, what do the different Ds designed for help us in improving this figure? So design for recycling alone helps us, in most cases, today at least, into this direction. It does not necessarily lead to more usage of recycled plastics. So if we would like to achieve this, we need to increase and to use design for circularity. And there's also design for functionality, which means that how do I create a package with the least amount of substance or materials with maximum functionality, and obviously this leads to a reduction in the material usage. So if we would like to reduce the amount of fossil-sourced material, we have to improve this, and we have to improve also the functionality. So this is, by the way, the reduce R of the many R's that are used for the EU targets. Okay, this is the aspects: design for recycling, design for circularity, and design for functionality. And you will see in the end that design for circularity and design for functionality may have synergistic effects. Yes, but the question is always, that has been posed several times already today and in many other occasions: why should we use packaging plastics after their usage, again for packaging and not for other purposes? Because if we want to reduce the fossil input, we can also imagine to reduce the fossil input for agricultural films. Why? To packaging. And the reason is, I try to make it clearer. If we look into all packaging, all applications of plastics, these are again the figures from Plastics Europe, valid for 2020. If you look in comparison to the plastics that are used in packaging, you will recognize that packaging plastics are composed of those 5 major elements: LDPE, HDPE, polypropylene, PET, and polystyrene. And it's more than 90% that is composed from these plastics. So if you right now try to recycle them, you will recognize that those plastics are used for 60% of the cases are used again for packaging. So if you try to look at the single figures, you will see that more than 60% of the LDPE is used for packaging, more than 50% of the HDPE. Only polypropylene is different. It's less than 50%, but PET close to 100, and polystyrene again more than 50%. So if we try to find a market for recycled plastics, we will not be able to raise the recycling content above a certain figure, because we need to go into packaging. Otherwise, the market is not big enough on the long term. This is something that's easily forgotten, and this is one of the reasons why the EU set these targets for recycled content. And also the brand owners play their role. So, okay, we may think about or discuss whether these figures are realistic or not, but they are on the market, so to say. So we have to think about how to achieve them. So I come to my next point. How do we assess the recyclability of packaging materials or of packagings? We have the draft for the Plastics and Plastics Waste Directive, where it's a simple mass-based classification. If a packaging contains more than 95% recyclable content, it gets grade A, and so on. Something else, something about reusability in packaging applications, completely missing. We have the most elaborate recyclers classification, which is, let's say, the standard today. Here we have levels A or B, which may be leading to closed loops, possibility, slight restrictions, and we have the other classifications going down to level F, which is not usable for this kind of recycling. Okay? Do you find something like applicability in food packagings? No. We have incompatibility lists, which are in the German packaging law. Some examples just for illustration. For instance, PVDC layers are ranked as non-compatible, or some silicone components of PE containers. There's a detailed list about this. So it's a negative list. This should not be used for recyclable packages. What should be used for packages that are usable to make food packagings again? No information. And there's a lot of other guidelines, but all these rules and guidelines don't tell us what we shall do if we would like to reuse plastics in food packaging. Okay, if we want to use recyclates in food packaging, we have the applicable EU rules. You all know them, and you also know, and we had already discussed this several times already today, that these rules are in apparent contradiction to the proposal that's been introduced right now with its recycled content targets. So we have a lot of problems. Yes, that's true. And this is a point to be solved. We can complain about this, but it's, to my opinion, better to look for solutions for this. So just to remind you of that, what most of you will already know, the central issues of the regulations concerning food contact is that the packagings have been safe. To be safe, we have this union list, we have the treatment of the non-intentionally added substances that are created in recycling processes, for instance. And we have the option of using functional barriers. And I will tell you a little bit more about this in a minute. Nevertheless, there are two figures that are valid at the moment. 1 milligram per kilogram of food if you use a functional barrier, unless the substances are CMR substances. But if they are CMR substances, the daily intake that has been set up is much, much lower. So if you have a number of thousands or even tens of thousands of substances that may be in a recyclate, how do you know whether they are CMR or not? Difficult to analyze. There are some techniques, I will not talk about them for time reasons at the moment, but you need some options to get very low levels of substance transfer to the food. And this can be done, but I will tell you also, you have to be very careful about saying so, can be done with functional barriers. So functional barriers are not the solution for everything, but they are one part of the solution. The other part of the solution is to avoid specific contaminants. And the key is, in the end, we will need both. Okay, how does a functional barrier work? Very simplified. So this is a contaminated polymer layer, and this is the amount of substance that goes out of it over time. Here, in the end, you will reach an equilibrium between the material and the food, which is given by the so-called partitioning coefficient. Well, what happens if you cover the contaminated single polymer layer with another polymer that has a lower diffusion coefficient? This could be named as a functional barrier. The problem is if you co-extrude this, you put both polymers through, in their heated liquid form, through a die where they get in first contact. And just upon starting with this contact, the migration will start. And the temperature is much higher. The mobility of the molecules in the liquid state is far above that what's in the solid state. And we have a contaminated outer layer of the functional barrier. That means that also, even though the diffusion coefficient of the functional barrier is lower than of the polymeric carrier, also there you will start with substance transport from the beginning. It's less, but that's all. If you wait long enough, this curve will go up and will reach this equilibrium as well. So the functional barrier, the simple functional barrier like this, only gives you some time, some extra time. But if you have a functional barrier that is not contaminated from the beginning, you have the so-called time lag, which helps you a little bit. Depending on the nature of the contaminants, by the way, this time lag can be also 1 year, for instance. So it's not that bad. It's just a little bit small in my image, but it needs not to be very small. But it depends on the polymer and it depends on the contaminant. So you can say we may have a functional barrier, it may help us, but we have to avoid some specific misconceptions. For instance, the misconception that a co-extruded functional barrier is already a good functional barrier, which is not necessarily the case. Okay, we have other ways of making a barrier. We can, for instance, use inorganic layers, thin deposited aluminum layers, aluminum oxide, silicon oxides. I will show you some examples in a minute. How do they work? There's also a misconception. Many people think that these thin layers are a perfect barrier. They are not. They just reduce the amount of substance transfer by some factor. So we have again the figure here, the same type of curve as we had before with the contaminated polymeric barrier. And we can get, on the other hand, this lag time if we combine the inorganic coating with an organic, clean polymeric material. So we have some different principles for design of these layer systems, but we must be very careful to select the right ones. So the best would be to use this one. But in many cases, this is not possible because either it's rated to be too expensive or because other things are against this. But this is, let's say, the best you can achieve. If you would like to know the figures between this and this and this, you may, for instance, also have recognized that the slide Olivier Vitrac showed some hours ago are a little bit different because he compared the layer with a functional barrier with a film or material with reduced contamination. So the time behavior will be a bit different then, yes. But so if you compare his slides with mine, you will recognize that the basis of the comparison is different. Okay, so some realistic examples. This is not a functional barrier. If you just cover a high diffusive polymer with a virgin layer, this will be contaminated in the moment when you extrude it, and later on the diffusion coefficient of this material is simply too high to protect it, to protect the food. The PET can be used in this form, but not because there's another mechanism, but simply because the diffusion coefficient of the PET is so low that it reduces the transport from the beginning, and just the total figures are lower than with this example. So we had the same argument for the polystyrene in the presentation before. It depends on how much time you have. So the shelf life of the product is a decisive factor, and also the amount of contamination here. Others talk about this kind of barrier layers: polypropylene, EVOH, and a sealable propylene ethylene copolymer. This could be recycled. The question is it really a functional barrier? If you co-extrude it, and if you use recyclate material here, probably could be, you don't know, it depends on the circumstances. If you use a virgin type of material of this as a barrier layer against a contaminated paper, then it's an excellent functional barrier, simply because you started then with a clean polypropylene. This would be something that could be viable. You use recyclate material and you coat it with silicon oxide on the outside. Some bottles or cups are made by this way. And this is the triple layer: the inorganic barrier layer, an adhesive in addition, and an outer carrier that helps to make the best barrier available if you don't use an aluminum foil. So you have some options, but also many restrictions you have to think about. So finally, if we apply these techniques, they give us one benefit, which I want to talk about right now. And this is the functionality for the packed food. You know, most of you will know that water vapor transmission and oxygen transmission are important factors for the functionality of a packaging, and that we need high barriers against those two substances for many applications. So my usual simple figure to demonstrate this is to plot the water vapor transmission rate and the oxygen transmission rate, and to put in the areas, the regions that are required for some different types of foods. And this is, so to say, the area of sensitive foods, which is in many cases very important to be achieved. And if you look to the usual polymers, you recognize that some polymers are able to maintain those limits, while others, especially the dominating polyolefins, are not. So, on the other hand, we would like to make monomaterials, so-called monomaterials that can be easily extruded in mechanical recycling. Those up here. And they don't have the sufficient barrier. So if we apply this principle of functional barrier with help of those inorganic barrier layers and this kind of structures I showed you before, we can achieve an improvement by up to a factor of 100, which helps us as well in achieving those target figures for the product functionality, and at the same time, this can help us as well to reduce the material thickness. This is a special approach which may help us to achieve some of the targets that are given to us at the moment. Some conclusions right now at the moment. We will need more recycled content not only for PET containers, where we today already know that it can be achieved. The barrier technologies can be applied to achieve them, but okay, and at the same time, they can help us to reach the functionalities with monomaterials that we need to get. But we still know by far not enough about the constituents of packagings and their evolution and their reactions in the whole process chain, including the recycling, to really understand what is happening there. So, for instance, we know by several experiments adhesive and especially printing inks may be detrimental and create a lot of additional substances that give us a lot of problems, even so many that even a functional barrier will not help. So this needs to be investigated more. And also the sorting, and we talked about this already several times today, sorting between non-food and food containers by different methods. This is something that needs to be investigated in much more detail. So, in total, we can say the whole packaging circle needs to be investigated, and this brings me to my last slide. Unfortunately, there have been some more green lines showing to everything. I will explain you what this complicated image means. We are right now in a very big German national project with more than 60 partners trying to image the whole recycling chain or the recycling circle over the production of packaging, the packing process itself, the collection afterwards, the whole different steps in the recycling up to the reuse of the recyclates in the production of new packaging. And there should be a lot of green arrows, and I made, you can see something here. My problem was I made them too distinct, so they should be black, then they would have been transported by the automatic tool that Olivier and his co-workers created. They simply lost. Sorry for that, but just think about a lot of green arrows going from this central data space that will be just created in the course of this new project. We started it in end of last year. And we will try to look how artificial intelligence is able to link all these different steps. And in the end, I think you will expect the same. We will still not have the solution, but we have a better image of what is happening there. And unfortunately for you, Olivier, this was a national project. Otherwise, we would have been applied together, I think. Yes, that's my final slide. Thank you very much for listening. And I hope you still have some strong oppositions against something that I mentioned.
Thank you for the presentation. I have no opposition, but just a question about functional barriers, dealing in particular with very thin layers that we can deposit on the surface of food packaging. And we're talking about several tens of nanometers, which is very, very thin. So there is an experimental difficulty to deposit. Do we have already the industrial scale-up for that to get an homogeneous layer in order to get the functionality? And second aspect is, as it is very thin, do we know already about the mechanical impacts and defects that could be created during the use of this kind of packaging?
Thank you for this question, because this gives me some more minutes to explain. We have two methods to apply these layers. One is on films, and if you apply them on films, they need to be protected afterwards, because you cannot use such a film in packaging without an additional top coat from a polymer. So this is why I also showed this combination of thin layer and also an additional polymer on it. This kind of layers is being made since 30 years in big machines, delivering some 60 kilometers of film per hour, for instance. But they have to be improved still. And their thickness has to be reduced just also to make sure that the scale is still economic. The thickness of 80, 60, 40 nanometers is state of the art. This is not a problem, and they are coherent. Everything is safe there. If you would like to go below this to, let's say, 10 nanometers, it will be a problem, and this is something we are just working at. This is not industrial reality today, but the rest, you can buy it. The other technique is to coat the inside of containers, be it cups or bottles, for instance. This is something that's already also available on the market, also with a thicker, 80 nanometers. It's still extremely thin, but also there we need thinner layers for economy and also for many other reasons. So the thicker layers can be applied, and you can buy equipment that's able to do it. And these kind of structures, they can work with just one layer on the outside without additional protection, because it's in the inside of the container. So this has also been proven to be sufficient so far. Also, Roland Franz and Frank Welle published the first results of the functional barrier of such construction 12 or 13 years ago. Okay, so this works, but it still has some additional challenges to reduce the thickness.
Thank you so much for your presentation. What about the recyclability of this new package? And with time, how we are going to have more and more of these packagings, how all the cycle goes around?
Yes. There's two aspects of this. And with the containers, we are talking about maximum of 60 nanometers, for instance. If you relate this to the whole amount of material that's being involved, let's say 300 micrometers of plastic, then the amount that the relation between the coating and the polymer is so small, coating versus polymer, that it does not harm the recycling process. Even you can just calculate, even after 10, 20, 30 recycling processes, you will be far below the usual amount of small-scale additives in plastic. So this is not the problem. The problem in the film laminates is not the layer itself, but the adhesive. So what about the products the adhesives create upon being recycled? This is the major issue, and there we still need some technical development if we would like to raise the figures for recycled content.
Thank you for your presentation. Sorry. Yes, one more quick question. Okay, this is me. Thank you for your presentation. I'm really happy to see someone else working on functional barriers. There is a problem with functional barriers also, is that as soon as the recycled material is in contact with a functional barrier, the contaminants that are in the recycled material starts to migrate. And for example, when I buy my packaging, I don't know where it has, when it has been manufactured. So do you think there is a way to control this, to control the span life of a functional barrier and be sure that when I buy my packaging, it's not already too much contaminated?
Well, it depends on at which place you put on the functional barrier. So if you, for instance, make sure that you always put the functional barrier on top of an intact, non-contaminated polymeric barrier, then you have done enough. But if you are not able to make sure that this happens, it's more difficult. And so after usage, you will have the mixture of the functional barrier and all the other things. If it's an inorganic functional barrier, you don't have an effect of it. It's practically inert. If you have an organic component of the functional barrier, you start running into problems, especially when it's a reactive layer of an adhesive. And in such a case, you must make sure that, especially when there are CMR substances involved, you must make sure that you apply the functional barrier only after the extrusion of the recyclate and not in extrusion of the recyclate, which makes things more complicated and more expensive, by the way.
Thanks again.